Earth's climate system. Earth has a global climate system that includes air, land, liquid water, ice, and living things. The climate system is powered by energy from the sun. The sun emits different types of radiation. So we get UV rays, which is ultraviolet radiation, visible light, and infrared radiation. When the sun's radiation reaches the Earth, what happens is some of it's absorbed, 70%, so most of it, and some of it's reflected back. And when you look at this picture here, what we see is, all right, here's 100% of the incoming rays, and 6% is reflected by the atmosphere. We have another 20% reflected by the clouds, and then we have a little bit, 4%, reflected by the surface of the Earth. So it depends on what's on the Earth. If it's ice, it reflects really well. If it's just sand, not so much. And then the rest of it is absorbed. The balance of energy on Earth. Earth behaves like the lamp and gravel model. So when you come to class tomorrow, what you're going to do is this experiment here, where we're going to shine a lamp on different kinds of gravel, like white rocks, gray rocks, black rocks, and we're going to see, okay, how does it heat up. But in the meantime, Earth's surface absorbs energy from the sun and gains what we call thermal energy. So thermal is that heat energy, and it warms up. Earth's warm surface emits infrared radiation back out. So we have this balance. So we're getting warm, but we're also releasing back out this infrared radiation. And it has to be a balance, because if this one was larger, Earth's temperatures would continue to rise, and we just get warmer and warmer and warmer. If this one was bigger, if we were giving off more, we would just get colder and colder and colder. So it says the amount of energy Earth's system absorbs from the sun equals the amount of energy radiated by Earth's system. As a result, the Earth's global temperature stays fairly constant. The complete picture includes energy radiated by the sun and energy radiated by Earth. So there's a balance. So, and it has to be that way, because if all of a sudden all we're doing is receiving, the temperature is going to go up. If we just give off energy, then the temperature is going to go down. So we need to realize how much we're absorbing in should equal how much is given off. Latitude and climate zones. Latitude is measured from the distance from the equator. Okay, so a small latitude means you're really close to the equator. A bigger number would mean you're further away from the equator. So it says, recall that latitude is one of the factors affecting climate zones. So it's not the only factor, okay, but it is one of them. So when we're closer to the equator, things are warmer. It says the climate is warmer at lower latitudes close to the equator and colder at higher latitudes more far away from the equator. And there's a reason for this, and this picture actually does a really nice job showing it. So if we had, say, this is about a centimeter of the beam sunlight hitting the Earth, and what we see is it hits a really small surface area, okay, when you're close to the equator. However, that same centimeter worth of sun hitting the Earth, if it hits it at the poles, okay, you almost get like a little cross section, and it's hitting a very, very large area. Now, it's the same amount of energy, which means the same amount of energy is spread over a larger area, so it's not going to heat up as much. It's almost like taking a magnifying glass and focusing all the beams in one little spot. It's going to get very, very hot here in the spot at the equator. However, on the poles, where that same amount of energy is spread out over a much larger area, okay, it's not going to get as warm. So near the equator, the sun's energy is more direct and is spread out over a smaller area, and therefore is more intense. Near the equator, the sun's energy passes through less of the atmosphere. Less energy is absorbed by the atmosphere and more reaches the Earth's surface.